Hi, I'm Michael Osman of Great Scott Gadgets, and this is Software Defined Radio with HackRF, Lesson 7, Complex Numbers in DSP. In this lesson, we'll talk a little bit more about complex numbers and why we use complex numbers in digital signal processing. Let's start by reviewing the homework from Lesson 6. For this exercise, I'm using IPython Notebook, which is a convenient way to use the Python programming language. You could complete the Lesson 6 homework assignment using any programming language, but I'm using Python for a couple of reasons. One reason is that Python is one of the languages you can use to write GNU radio programs, and in future lessons, we'll look a little bit at how to use GNU radio from Python. And another reason I like to use Python is because of IPython Notebook itself, which is a very convenient way to interact with Python, and it's a nice way for me to show you what I'm doing. Now, the Lesson 6 homework assignment was a problem that I asked you to solve. I asked you to create a program that would compute the average of a set of wind direction readings. And so one way you might approach this problem would be to create a function. I'll define a function called average, and the input to the function will be readings. Now, how are you going to solve this problem? The first solution that you might try is to simply take a simple average or a mean of the inputs. So one way to do that would be to start with a total at 0 and then add to it. This is kind of a verbose way to solve this problem. I'll say for r in readings, which means I'm going to loop through every reading, no matter how many there are, and in this loop, each time I'll set r to that particular reading. And then I'll take total and add r to it. So at the end, I can return a result, which is return total divided by the number of readings, or the length of readings. Now this is just a simple average. We add them all up and then divide by the number of readings. So let's see what we get when we try this. If I call this function average, I'll call it with the first list of readings that I told you to try. 12 degrees, 15 degrees, 13 degrees, 9 degrees, and 16 degrees. And the function returns 13. And that looks like a pretty good result. Now let's try the second set of readings I asked you to try. 358 degrees, 1 degree, 359 degrees, 355, and 2. And what do we get? 215. That's interesting. And I would say that's completely wrong, because if you look at these numbers, they're all very close to 0, or very close to 360 degrees, which is the same as 0. And then we take the average and we get this number 215. Well, 215 degrees is nowhere near 0 degrees. It points almost in the opposite direction. Let's see, average, let's try the third one. The third set of numbers I asked you to try was 210 degrees, 290 degrees, 10 degrees, 90, and 170 degrees. And these are kind of all over the place. And the result it gives us is 154. And off the top of my head, without doing some more math or drawing this out on a piece of paper, I can't really say how good a result that is. So we clearly have a problem here with this particular input, this particular set of inputs. And one way you might think of to solve this problem is to normalize the input so that maybe instead of 358 we say -2. -2 degrees, this should be the same as 358. Or on the other hand, maybe we could leave that as 358, and instead of saying 1 degree we could call this 361 degrees, and then maybe that would work. Let's try one of those approaches. If we just put a conditional in here, if r is greater than 180, say, then we'll subtract 360 from r. Let's see if that works. Now, if I execute the first yep, the first set of readings gives me the same result, 13. And the second set of readings gives me -1. Hey, that looks good. That's very close to 0. -1 degrees. That's the same thing as 359 degrees, which is right there. And let's see, the third set now gives us 10 degrees. I'm not really sure if that's good or bad. Let's try another set. Let's try something that's near 180 degrees. 170, 171, 180, 181, 190. So we should get a result somewhere around 180 degrees. And we don't. We get 34. Now why did that happen? That happens because we took the problem here, the problem that we had around 360 degrees, we shifted that problem around. We avoided it by shifting it over to 180 degrees. Now when we have results or inputs around 180 degrees, this thing goes haywire. Now hopefully some of you tried this approach and at least got this far to recognize that using the method of a simple average is not correct for this problem. And if you came up with an actual solution for this problem that works with all possible inputs, then I think well, what I've seen, the only solutions I've seen that actually solve this problem are solutions that take into account the two-dimensional nature of these directions. And in general, the right way to approach this problem, I think, is to approach it as a vector addition problem. So the error here in our method, I think, is right here. We add up all of these values as if they're one-dimensional, but they are in fact two-dimensional, or vectors. So I'd like to show you my solution to this problem, and to solve this, I of course use complex numbers. You don't have to use complex numbers to solve this problem, but I think that complex numbers make vector arithmetic very easy, and it's a convenient way to conceptualize how to solve this problem. So let me show you what I do. The first thing I would do is to import CMath, or import the complex math library, and then define tau to be equal to 2 times pi. I have a lot of programs that start this way. Now, I will use the same function name, same inputs, but I'm going to start by defining a base. I'm going to exponentiate this base. I'm going to use a method of complex exponentials. And the base that I'm going to use is e to the, and then the stars here are the double star operator in Python is the power or exponent operator. So e to the 1j, and 1j in Python is the imaginary unit. So you can think of that as pi. Now if I just stop there, that would be, this point, this base would be a complex number that is on the unit circle and is 1 radian around the unit circle from the positive real axis. If I multiply that by tau, that makes it 1 turn around the circle. So this ends up back at 0 degrees or at 1. And then if I divide that by 360, now I'm dividing the angle of the unit circle. I'm dividing a complete turn into 360 parts. In other words, base is now the complex number that is on the unit circle and is exactly 1 degree of rotation above the positive real axis. And this is a very convenient base to use if we want to manipulate degrees. So I'm going to take the same method and start with total, and I'm going to take a simple average, but now the average is going to be of these complex numbers instead of being an average of degree measure. I'm going to not do this trick that didn't work. And instead of adding up r, I'm going to add up base to the r. So if r is 1 degree, then I'm adding the complex number, or the vector that goes from the origin to that point that is 1 degree around the unit circle. If r is 45 degrees, then base to the 45th power is the complex number that is 45 degrees around the unit circle. And then I don't want to actually return the complex number result. I prefer to return a result that is in degrees and is the real value result. So I'm going to add an additional step here and say result, or my resultant vector, the average, is equal to total divided by length of readings. Same expression we used before, but now the actual return value that I'm going to use is cmath.log. Wait a minute, what am I doing here? I'm taking a logarithm of the result. Now remember that a logarithm is the inverse operation of exponentiation. So if I take the base to a power, and that power is a number of degrees, to find some point in the complex plane, then to reverse that operation, if I have a point in the complex plane and I want to find the number of degrees, then I use the inverse function of exponentiation, which is a logarithm. And I use the log function from the CMath library specifically. And I'm doing one thing wrong here I have to fix. I want this logarithm to be with respect to my base. So it's a logarithm base this thing. Now let's see what result we get. If I execute this function on the first set of readings, which previously gave me 13 when I used a simple average of degrees, now I get a number very close to 13. However, it has this extra little imaginary component. And the reason it has this extra little imaginary component is because my result isn't actually on the unit circle, and I'm doing a complex logarithm that is with respect to a base that is on the unit circle. So there are a number of ways to correct this problem, but notice that just the real part is basically the answer we were looking for. And so for now, I'm just going to say that a good way to, or an acceptable way to solve this, avoid this problem with this complex result, is just to take the real part of the result and ignore the imaginary part. Now let's see what happens when I try it on these other sets of inputs. This one here that seemed to be about -1 degree. Sure enough, I get a result that's very close to -1 degree. And this one, with numbers that are all over the place, this gives me -170 degrees. That's the same as 190 degrees going in the other direction. And this one that should be somewhere near 180, I get 178 degrees. That looks pretty good. I think we have now a function that does the job. This is one way to solve this problem. We're doing vector addition and then taking the average of those vectors and then using the logarithm to convert back from that vector in the complex plane into a number of degrees. And we're using this trick of using exponentiation and logarithm with respect to this base, this special base. Now the second thing I asked you to do in the homework assignment was to also consider the wind speed in addition to the wind direction. So one way that you might do that would be to maybe make your list of readings be something that includes both speed and direction. So you might specify, instead of specifying 12 degrees, maybe you specify 12,1. And that's, say, 12 degrees of direction and 1 mile per hour, or whatever unit you're using. And then 15 degrees, 1. Each of these is a pair of values. And if we give them all the same value, we should end up with the same result that we had before. If they're all equal to unit speed, we should get the exact same result. But if we enter in different speeds for different directions, we should weight the result toward that direction. So I'm going to use basically the same approach, except here when I take a total, when I exponentiate my base, I'm going to say, instead of r, I'll say r sub 0, which is the first part. It's the 0th index of this pair. So r0 is this 12 degrees. And then I'm going to multiply this base by r sub 1, which is the second number. r1 is the second number in a reading, and that's the speed. So notice what I'm doing is I'm just multiplying or scaling this number in the complex plane. I'm scaling that vector by the amount of speed. So I'm increasing its distance from the origin if the speed is high, or I'm reducing its distance from the origin if this number is low. And then I'm going to use the same approach, take a simple average of these vectors, and they're two-dimensional values, not one-dimensional values, and see what we get. So theoretically, this should give me the exact same result that it did before, and it did. And if we weight it, let's say we had a big gust of wind when it was 9 degrees. Let's see what happens. Look at that. My average reduced closer to 9. This seems to work. Now, interestingly, I'm only returning degree or angle information here. But what happens if we also return the speed, or the average speed? What I'm going to do is take the absolute value of the result. That is its distance from the origin. So if I return that as a tuple, now my result is 10 degrees with an average wind speed of 2.8. If I set this back to 1, and all of them were about 1, then my average should be near 1. It is very close to 1. Now let's see what happens. I'm going to try these other values. And I think I'll skip ahead in the video here so you don't have to watch me type all of these. Now let's try this new function on all these other inputs. If I take this one, I still get a direction very close to -1, and I get an average speed very close to 1. That makes sense. Now I'll try this third set of inputs. Now I still get the same average direction of -170 degrees, but now look at the average speed. The average speed is very small. It's only about 1/10 of a unit of speed. And if you think about what's going on here, what we're doing is we're taking an average of a bunch of vectors that are going all different directions. And it turns out that their result is pretty close to the origin, which means that this average direction of -170 degrees is a weak result. And so this actual output of speed, or the magnitude of the average wind direction and speed, actually gives us some indication of how much overall wind motion there's been, or how much average motion of air there's been. And since it's moved a lot in different directions, those different directions have canceled each other out, and we end up with a very small average or a weak result. Now, maybe it was a really gusty day. Maybe this was 3 miles or maybe 15 miles per hour that direction, and 10 miles per hour this direction, and 1 mile per hour in that direction, and maybe 3 miles per hour in that direction, and 6 miles per hour in that direction. Now in this case, we end up with a different result vector that is -138 degrees. It's a little bit of a different direction, and a much higher average here, because we have more speed going roughly the same direction, and then weaker speeds when we're going different directions. So this whole approach of doing vector addition gives us a really nice indication of perhaps a confidence value, or an average air motion in this case. Now let's try it on this last set of values. I end up with a very similar result, 178 degrees, and the average speed of 1, unless I tweak some of these, then things change a little bit. Now, I'd like to plot this a little bit and just visualize so you can kind of see what's going on here. And I'm going to use matplotlib. And I'll just type a little bit and skip the video ahead so you don't have to watch me type all this. Now my function returns the exact same thing, but I also plot a couple of things. I plot each input vector, and I plot the result vector, or the average of all of those inputs in the complex plane. Let me show you what happens when I try it on this first set of readings. Here we go. We get a bunch of red inputs that all extend from the origin in roughly the same direction, and this blue result is right in the middle. And if we play the same trick of making these different values, then maybe we'll make this one 0.5 and this one 0.2. And now you can see we get different little vectors here, but their average ends up in roughly the same place. Now let's try this next set of inputs. In this case, again, we have a bunch of readings that are clustered around 0 degrees, or clustered around one place, and we get an average, this blue vector, that points in that direction. And for this third set, now we have numbers that go all over the place. And you can see I'm going way off the screen here because I'm using some numbers that are much larger than some wind speed numbers that are much larger than our original ones. But let me just try kind of putting these all into scale here. Now you can see if these different wind speeds, if these different wind measurements had different speeds, then the preponderance of the wind, or the average air motion, is in the direction of the blue vector here. But if these all have the same speeds, or if we have no speed information, and we just have to assume that they're all the same, then we end up here with all of these input vectors at the same distance from the origin, but the output vector is very, very weak and in a slightly different direction. And if we take all these numbers that are near 180 degrees, we should see, yes, they all point to the left. And if I give them all the same magnitude, or the same distance from the origin, or the same wind speed, then this is what it looks like, and we get this blue vector resultant right in the middle. My approach to solve the Lesson 6 homework might not be the best approach or the most efficient approach, but I think that it is a conceptually interesting approach. I think it's great that we can use complex numbers to express the solution to this problem in Python. Now, I'd like to talk about why we use complex numbers in digital signal processing. Hopefully you've gotten a little bit of a taste of how complex numbers can be useful, but you may still be wondering why we use them so much in digital signal processing. You've seen those blue inputs and outputs on blocks in GNU Radio Companion, on so many blocks. That's the complex data type. Why is the complex data type the default for so many blocks that are useful in GNU Radio? Well, there are a lot of answers to that question, a lot of reasons why complex numbers are useful in digital signal processing. One of those reasons has to do with the hardware, and HackRF and other software-defined radio platforms are quadrature sampling systems. That means that the input and output over the USB connection is actually a series of complex numbers. So that's something that we'll talk about in the future, the architecture of the hardware and why quadrature sampling is useful. But that's one reason that we use complex numbers in digital signal processing, because that's what the hardware gives us, or that's what the hardware expects when we want to send samples for it to transmit. Another reason that we'll talk about in more detail in the future has to do with the FFT. you've seen the FFT algorithm in action using the FFT GUI sync in GNU Radio Companion. And the FFT is a wonderful and interesting algorithm that we'll talk about in more detail in the future. But something that you should know about the FFT right now is that the FFT is inherently a complex function. It takes complex input and it gives complex output. And when you use the FFT sync in GNU Radio, what you're seeing is a display of the magnitudes of a bunch of complex numbers. We're throwing out the direction information and just showing the magnitudes. And for the rest of this lesson, what I'd like to talk about is some specific examples of modulation, how we encode information on radio signals, and how we can decode that information by demodulating radio signals. The first modulation I'd like to talk about is amplitude modulation, or AM. The way that AM is traditionally visualized is as a sinusoid that varies over time. And if I do a good job of drawing it, you should see that the amplitude changes over time, but the frequency should not. So the peaks should be at approximately the same amount of time along the time axis from one another. So the frequency doesn't change over time, but the amplitude does. And specifically, what we see is this envelope, or the bounding function around the sinusoid, is something that changes over time. And this envelope is what actually carries the information. Now, it might be an analog envelope, like AM radio that you listen to that carries audio. That's an analog audio signal that is used as the envelope function. Or in this case, what we might have here is a digital signal. Maybe this is a 0, and then when the amplitude is high, it's a 1, and then this is a 0 over here, and then another 0. That would be what we'd call ASK, or amplitude shift keying. Amplitude shift keying is just a name for digitally encoded data, or it's the modulation in which we use amplitude to digitally encode data. Now, remember that in a software-defined radio signal, what you actually receive in software is a series of samples at discrete points in time. And so think of every little red X here as being a number. Sometimes it's a positive number, and sometimes it's a negative number. But what we get if we're trying to build a software-defined radio receiver is a series of numbers over time. Now, what I want you to imagine for a moment is that you're designing a software-defined radio receiver, and you receive this list of numbers, this sequence of red X's. How would you recover the information? How would you demodulate this sequence of red X's to reproduce the envelope function and determine whether a 0 or a 1 was sent at any particular point in time? Think about that for a moment. Can you propose an algorithm that you could use to take this list of numbers and turn it into the data that were originally transmitted? One thing you might think of is to rectify the signal. And a way that we do that in software is by taking the absolute value. So the positive values are unchanged, but the negative values are mirrored across the time axis and become positive values. This is an absolute value function where we just take the magnitude of each sample and take it as a positive number every time instead of a negative number. Now this is one way to rectify the signal, and you may have heard the term rectification from analog electronics, where people might use a diode, for example, to rectify a signal, instead of here in the digital domain, where we might use something like an absolute value function. So that would be a rectified signal. However, we still have this problem where what if we look just at this sample right here? Well, it looks like 0. But is the amplitude 0 at that point? No, it's not. What we really want is the envelope, not that particular 0 value. That 0 crossing might mess us up. So what we really need to do then is to take a rolling average over time, an average of these samples, so that the average over time is going to look something more like this envelope curve. But in order to do that, we have to average several samples in a row, several of these dark blue x's in a row, in order to produce one x of average. So how many samples in a row do we have to compute this average over? Well, in this case, it looks like we might have to compute it over at least 4 or 5 samples, but it all depends on your sample rate and the frequency of the signal, the carrier frequency we call it, and the ratio between your sample rate and the carrier frequency. If the sample rate is very high compared to your carrier frequency, you might have to do this averaging over a much larger number of samples, maybe tens of samples or hundreds of samples or even thousands of samples. And that is a lot of CPU power that you need just to produce one output sample that tells you that we have a 1 that was transmitted instead of a 0 that was transmitted. It's a whole lot of processing. Now what I'd like you to do is to imagine that this is represented as a complex number instead of as a real number. So instead of seeing a sinusoid, imagine that that green curve is actually a helix, and you're just looking at it from the side, and the helix grows larger and smaller over time. Now if you look down the time axis, we can plot this in the complex plane. And what we should see is, instead of something that looks like this, varying in this just one dimension over time, we should see something varying in 2 dimensions over time. And it has a low amplitude or a low distance from the origin, and then it becomes a higher amplitude. It's bigger around, and then it becomes a lower amplitude again, and it's a low amplitude for a long time, and we see something that looks kind of circular if we look down the time axis. But again, remember that what we really get is a series of samples over time. So if it were to be a low amplitude for a while, we'd get a series of samples like so, and then if the amplitude were to increase, we would see a series of samples like this. And eventually, if we keep going around, we'll get samples that are low again, or have a low magnitude. They're closer to the origin here. Now, if we were to represent this signal as a series of complex numbers like this, instead of representing the signal as a series of real numbers, now can you propose an algorithm that you could use to extract the envelope information? Think about this for a second. How many samples do you need at a time to compute the distance from the origin? Notice that we no longer have this 0 crossing problem. This signal never actually goes through the origin. And so all we need to do, if we want to demodulate or recover the amplitude information over time, is look at this distance from the origin of this one sample. Then look at the distance from the origin of that sample. Then look at the distance from the origin of that sample. If we think of each of these as a vector and just take its distance from the origin, now this sample is a little bit bigger. This sample, now we seem to have a high amplitude. So this may be this region here where we had a 1 transmitted. And eventually we'll go back to a lower amplitude. Now how do you compute the distance from the origin? Well, it depends on how your sample is represented. But if you have IQ, quadrature information, then what you have is you can think of as a horizontal component and a vertical component. You have rectangular components. So if we wanted to find this first sample here, take its magnitude, or its distance from the origin, then we would take its I value, which is this horizontal component, and then its Q value, which is vertical component, and we could use the Pythagorean theorem, and this distance from the origin would simply be the square root of I squared plus Q squared. Now think about this for a moment. How many samples at a time do you need in order to compute this? Remember that up here we needed to average several different absolute values of samples together. And it may vary how many samples we have to average together. It could be a whole lot of samples at a time that you need to get one output value. How many samples at a time do you need to compute this algorithm over in the complex view of this signal? It's only one sample. You only need to compute this over one sample at a time. And here's something that could make this algorithm even simpler. Notice that the only really hard part is taking the square root. Squaring a number is very easy for a computer to do. Adding two numbers together is very easy for a computer to do. But taking the square root is harder. And it turns out that in many cases we can just skip that step. If all we're doing is comparing the result to a threshold, then it doesn't really matter if we have the magnitude or if we have the magnitude squared. So we can skip that and just compute I squared plus Q squared, or the real part squared plus the imaginary part squared. Isn't that an amazingly simple algorithm to demodulate a signal and recover this envelope over time? I think that's pretty neat. The next modulation I'd like to consider is frequency modulation, or FM. The way that FM is traditionally visualized is again as a sinusoid over time, but this time instead of the amplitude changing, we'll see the frequency change. We'll see a shorter period, and if I've done a good job of drawing it, then you should see that the envelope does not change over time. The amplitude is the same, but the frequency gets higher and then lower again. So remember that if we are building an FM receiver in software, we actually get a series of samples that are discrete points in time. Now, think about this for a moment. If you were to be given this list of samples, this sequence of red X's, some of them positive, some of them negative, what algorithm could you use to decode this information or recover the frequency over time? You should be able to recover a low value over here, and then a high value, a high frequency, and then a low frequency again. It may be the exact same information. Perhaps this is not ASK but FSK, frequency shift keyed information, and this is a 0 and then a 1 and then a 0 and then a 0. It could be the same exact information, just using a different modulation to encode that information onto this carrier wave. So you're given this series of red X's. Can you propose an algorithm that you could use to decode this information, to extract the instantaneous frequency over time? Now this might be a little bit harder than thinking about AM demodulation, but one thing that you might propose is to look at how often these peaks happen. Or another thing you might propose, like notice that these peaks are very close together and then they're further apart. However, that is potentially error prone if we have much noise in the signal. Another thing you might propose is to look at these zero crossings. How far apart are the zero crossings? They're closer together and then they're further apart. But again, things might be error prone. What if you have a little bit of noise in your signal? Each of these samples is randomly moved up and down a little bit. You might have some extra little zero crossing somewhere that could throw things off. So you have to do some kind of smoothing over time. You have to make sure that your signal is normalized so that you can, like if you're looking at zero crossings, you need to make sure that your signal actually crosses zero and doesn't do something like this, where it never crosses zero, or it just crosses zero on rare occasions. There's a bunch of work that you have to do, and every algorithm that I can think of that would do this for a real valued signal like this, without thinking of it as a complex number, I think would have to compute something over quite a few samples at a time, similar to the problem we had with an AM demodulator. And the amount of samples that you have to compute over at the same time is dependent on a number of factors that aren't entirely in your control, perhaps. So again, you might have to compute over tens or hundreds or more samples at a time just to get one output value, just to determine whether or not this is a 1 here versus a 0 over here. So now I'd like you to think of this as a complex valued system. And so instead of seeing a sinusoid, imagine that this is a helix, and you're just looking at the helix. This green curve is a helix that wraps around the time axis. So if we were to look down the time axis and look at our complex plane, we should see this curve does something like this. It goes around slowly, and then around faster, and then slowly again. If I were good at drawing, it would pretty much just look like a circle. But the rate at which it advances around the circle changes over time. Sometimes it goes around slowly, sometimes it goes around fast. And if there isn't very much noise in the signal, it should look very much like a perfect circle. So remember that this is going to be a digitized signal, and so you'll see a sample here, and then a sample here, and then a sample here, and so forth, while the frequency is low. But then what happens when the frequency increases? We'll see the next sample here, and then here, and then here. Notice that we move around the unit circle faster, or around the origin faster. From sample to sample, the angle increases. So now think about this. If we have a complex valued signal that is an FM radio signal, how would you extract the frequency information over time so that you could decode this signal? Well, the method that I would propose is to look at each of these as a vector and look at two samples in a row and measure the angle between them. It's a low angle, then it's a low angle, then it's a low angle, then it's a low angle. And the angle maybe gets a little bit bigger, and then quite a bit bigger. And now we're dealing with a very large angle from sample to sample. So this is the information that we're looking for right here in the angle. So just the only thing that we have to do to recover frequency information from this signal is to measure angles, or to compare the angle of one sample from the next. So one way you might do this is to take the angle of each sample with respect to the positive real axis here, this angle, and then take the next angle from the positive real axis and subtract one from the other. So it's determining an angle twice and then subtracting. Of course, subtracting is very easy, and determining the angle may not be. Remember that this is a IQ. So what we have at our disposal is the information of how far over this way and how far up this way this sample is here. And in order to determine the angle from those two numbers, I and Q, can you think of a way to do that? Well, one way that I used in my in my program that I talked about as my solution for the homework from lesson 6, one way is to take a complex logarithm of that particular point in the complex plane. And another way you might think of is an arctangent function. Either way, how is that going to be implemented in a computer? It's probably going to be implemented with a lookup table. So what we do in order to compute the instantaneous frequency at any given sample is to do a lookup for one sample, lookup for the next sample, and then subtract those two values. And the result is the frequency, or the instantaneous frequency, from sample to sample, or between those two samples, we get its instantaneous frequency. So how many samples do we need in order to compute the instantaneous frequency? We need 2 samples at a time. And then we can move on. We could start with these 2 samples, and then we can move on to these next 2 samples overlapping the first set of 2, and then we move on to the next 2 samples, and so forth. So we can get an output value for every single input value that we receive, or every single input value minus 1. And we only have to compute over 2 samples at a time. It doesn't matter what the carrier frequency is, it doesn't matter what our sample rate is, it doesn't matter how much noise there is. Well, it matters a little bit, but it's not going to throw off our algorithm as much as, say, spurious zero crossings would up here. So we have what I think is a much simpler algorithm, and something that can be computed very easily and very efficiently by a general purpose computer. The homework for this lesson is listed at greatscottgadgets.com/SDR under Lesson 7. And what I'd like you to do is to look for a couple of different blocks in GNU Radio Companion that do the exact algorithms that we talked about in this lesson. I hope I'll see you next time for Lesson 8.